So I'm here to present our results of what became known as the Lolo Creek pilot basin study that DNRC did. It was a collaborative project that kind of started in 2015-16 between DNRC and the Montana Bureau of Mines and Geology. And for many people here, you probably know about a lot of the problems on Lolo Creek, from fisheries habitat, different environmental concerns, water supply concerns, and then also a lot of the hard work that DEQ and Forest Service and of course the Watershed group has coordinated to try and fix a lot of those problems and impairments to the creek. And water supply was really the thing that was the kicking off point for this particular study that DNRC and Bureau of Mines and Geology were going to do. And that was based on an observation that the creek began to dewater down here, the lower ends, kind of at a higher frequency than folks remembered it drying up. You know, just in the last 20 years, it had started drying up more frequently than just maybe once a decade or even more. So I think the Watershed group and other stakeholders started to realize that, well, maybe we don't have a ton of information on the actual hydrology of Lolo Creek and water supply, where it comes from, how it's used, and where it goes. And so that was really the start of this project. And there were some changes that have been made along the way. It's obviously a multi-year effort. One of the big changes was, I think, funding issues that got in the way of the initial kind of collaborative and how the project was going to work, which didn't end up stopping the project. It just made it kind of drag on with these different routes for how things were going to happen. And so instead of this full-blown coordinated effort between the two entities, the groundwater portion was kind of shipped off to Bureau of Mines and Geology through their groundwater investigation program, which was nominated by the Watershed group and selected by them to study this lower half here, pretty much from the canyon down to the Bitterroot, and really dive into how the creek actually dewaters. What's the mechanism for loss to the groundwater, to the aquifer, and include other components of that. And then DNRC just kind of went on their own to do our half of it, which was to provide an entire basin outlook of water use and water availability, and essentially build what's called a water budget. And I want to really quick define that. Some people get stuck on the term water budget. They focus on that budget part and think maybe that's the state telling them how they can and can't use water, and it's not a method for allocating water to users at all. It's actually a hydrologic method that hydrologists use to track where water is in the landscape and at what time. So it's kind of like quantifying the pieces of a water cycle. You know, you have rain coming in and all these processes that happen in between before water ends up in the stream. I prefer the term water balance because that's kind of what it's like, balancing your checkbook. You're keeping track of water coming in and water going out, and it's more of just here's what's happening on the landscape, not a prescribing management to someone. That is done by DNRC, but that's through water rights adjudication and new appropriations. That really has nothing to do with this particular study. So aside from the funding issues that happened, I was hired. Some of you probably know Aaron Fiaschetti. He was the hydrologist that started this project back in 2016, and he went on to greener pastures with the USGS in 2020 when I was hired by DNRC and sort of took over the hydrology component of the project. And obviously with changing of hands, there's changing with methods and the way different people do things different ways, and so there's minor changes like that. But on top of that, we had a lot of these kind of water resources projects popping up all over the state at DNRC. It's not uncommon that our bureau, the Water Management Bureau, does these kind of basin water balances. And the reason it's called the Pilot Basin Study is because we've been playing around with some new sources of information and data, techniques, and modeling to really build more accurate depictions of how water moves through these watersheds across the state. And so Lolo became sort of an example of, well, let's experiment with new methods. They're not like groundbreaking scientific methods, they're just new to DNRC, so we have to kind of build a platform from the ground up. But in that decision-making process of, hey, we're going to do these new methods, let's test it out in Lolo, and then we'll hopefully develop a product that we can use all over the state to inform water resources a lot better. So we kind of split the project into two parts, and I'm going to present today as part one, which you can see at the top of these handouts, which I hope everybody got a handout. I should have checked that first, but we'll walk through the stuff in the handout. You don't need to get too focused on it yet, but this is basically just the hydrology and the water use of Lolo Creek from 2016 to 2019. Talk a little bit about the past, what data we had available for the past of what's going on in Lolo Creek, and then we won't really get into future stuff today. That's going to be part two, and I'll come back to that and actually talk more about that. But yeah, so the kind of structure of how I want to talk about these things, I'll go through how we actually do a water balance really briefly. We don't need to get too into the weeds on it. And then we'll kind of tell the story of how water begins, how it originates, where it comes from in Lolo Basin, and how it ends up here behind us in the creek, and all the different steps in between. And then also we'll talk about who's taking water out, where is it being used, how's it being used, and for what purpose. So really, there's a lot of ways you can do a water balance, ranging from really simple to really complex. And I would say for this particular project, ours is more on the complex side. So a lot of it is just collecting information. To put this together, you have to know what's coming in and what's going out, and that requires measuring it. Lolo Creek used to have USGS gauges occasionally scattered throughout time. Back to 1911, they put one in, and then they would take it out, and there was one in the 50s, and they were all kind of in the same location. But other than that, aside from Clark Fork Coalition, I think, measuring on the creek, there was not a kind of continually operating real-time gauge to measure flows. And there was definitely not enough gauges at the scale across the watershed that we needed to really dial in on these things. So that was the major component of data collection, was we had to go out and measure water in places and put gauges. The other component was measuring water going out, which was diversions. So we measured 4 major diversions, probably the largest on the creek. To get that information, we did what are called synoptic runs, which is you measure at key locations to try and track where water's coming in and out, all within a short span time, like a day. And that gives you a picture of what's going into groundwater and coming out of groundwater. So all that information we went out and collected in the field. And then there's another exercise where we go and collect information that other people have that we can use. So other things that we used were Lolo Water and Sewer District data on water use, like well pumping and things like that. We used parcel data for property boundaries and estimating lawn sizes for lawn and garden irrigation. We used census data because domestic use is tied to population, so we could look at population increases and use per person throughout the basin. And then some of the newer stuff we used was these gridded weather data. So it's not really weather data at a point, it's spread across the landscape, and you can get a better picture of how precipitation is spread across the landscape in little pockets throughout the basin rather than in just one rain gauge. And then probably the newest thing that was experimenting with this, we used satellite imagery to thermal imagery to look at temperatures on the ground surface and look at an energy balance way of determining how much water crops use. So that was what we used for the agricultural component of the project. And that's really it. If you look on page 1 of that handout, there's a map. That's our monitoring map. It has, I know it's kind of tiny on the page, but it has all of our stream gauges that we set out. There were 9 of them that operated for the 4 years. All the wells are the little orange dots. We have the kind of aquifer boundary on there. Little tiny green squares on there are the irrigated lands throughout the basin. And one important thing to note with the irrigated lands is you can see a bunch of them outside of the watershed. So that's something to remember. We'll come back to it later because it's kind of an important piece of the Lolo puzzle. So once we have all that information that we collect or that we go find that someone else collected, then it's pretty much an exercise of we have these governing equations is what they called, and we break the basin up into little sub-catchments based on where we have gauges, which is kind of like those Russian nesting dolls. You add them all up and then you get the whole basin, and that's really the process process that we followed for both tracking where water's at and then how it's used. So now that we know how we did that, we'll go into the results of what we found from the whole procedure. Starting with, we'll start off with the hydrology, which is just what are the kind of natural patterns and rhythms of water in Lolo Creek. And then we'll talk about the actual water balance and use, like where water is used. We'll kind of tie that all back together around this framework of these dewatering events that happen on Lolo Creek. So the story of how water gets in here, I'm sure, I guarantee everybody here maybe think 7th, 8th grade science class has seen a diagram of the water cycle. You know, you have the oceans, it evaporates, goes into the clouds, goes over land, rains, comes back to the oceans in a stream. Well, for Lolo Creek, you have to think that a cycle doesn't have an end or a start point, but we're looking at a little chunk of a cycle that has its own local cycle, sort of, but you're really looking at water comes into it and it flows out to the Bitterroot. There's no ocean down here that evaporates and recycles really back into Lolo Creek. So geographically, we're looking at just the basin and what goes into it, but there are still all these other processes that happen throughout. You know, you have evaporation, you have water that goes into the ground, you have water that stays in the soil, and then finally ends up down here. So the first component of that, I have my numbers here that I don't quite have memorized, but I want to be able to look at, sorry about that, is precipitation, obviously, right? That's the starting point when we're looking at this one little link in the chain. Because precipitation is how all the water that ends up down here gets there in the first place. So one note about precip here, generally in the Bitterroots, anywhere in the Rockies really, varies considerably with elevation, right? And this is a steep basin. You have a lot of elevation difference between where we're at now and Lolo Peak. And so there's two weather stations actually in the watershed. There's one operated by the Montana Climate Office right up here, a few miles upstream. And there's one at Lolo Pass. So that's an idea of what higher elevation looks like. But one thing to remember is the elevation of Lolo, the whole drainage, 45% of it is higher than Lolo Pass. So when you're looking at Lolo Pass, that's not even there's still a lot that's above that. And that's important because when you look at the average precip down here in the valley, it's about 16, 17 inches. At Lolo Pass, it's 45-ish inches. So you're looking at almost 3 times the amount of water that falls as precipitation up at higher elevation. We looked at patterns. We looked at the Snowtell site, which is the precip gauge up at Lolo Pass, goes back to 1983. So we looked at back to 1983 for any patterns that we could see. And then we looked at other longer term weather stations in the Bitterroot. There's not a ton of trend or change in precip amount. I mean, it varies from year to year, obviously, and maybe for several years at a time or a decade, but when you draw a straight line through it, it really doesn't have a significant, it's been increasing or decreasing for the last 50 years. But there are changes, and that's in the graph on page 2. We'll kind of walk through that because this one's an important one for precipitation. The changes are not with the amount of water that's coming in, it's how it's distributed throughout the year and in what form it's in. Precip here obviously falls as liquid rain or solid snow. So the top graph on there, the big one, and there's a lot of lines I realize and shading and a lot going on, but the lines basically are each year of this study. And it's a cumulative graph, so if it rains today an inch, you have an inch. If it rains tomorrow an inch, you have 2 inches. So it's just a way of showing you how much precip has fallen to this day, and it's since October 1st. For those of you familiar with a water year, they start October 1st, go to September 30th. Good question?
Precipitation, how do you measure it? Different gauges all the way down from the pass all the way down the creek? Or?
There's only 2. There's one at the pass and there's one down here. And they have standard weather service gauges that collect the water and filter out debris and condense it, and then they measure, the height of the water that's in it, basically. So that would be fall into that data that we went out and collected. We didn't collect the precip data. That was done for us by USDA and Montana Climate Office. And that's the graphs on here are the snow tell. So these ones are for, if you look on the left axis there, you're looking at 20 to 60 inches, so you're up at higher elevations. But the first thing you can notice looking at all those lines, if it falls in that green area, that's pretty normal. That's normal for 40 years worth of data. So the 4 years we did the study, precip was pretty normal or even above normal, despite having obviously years where the creek dried up, right? And the real, I think, meat of this graph is in the bottom two. And you can choose which one you want to look at. If you like rain, look at the one on the right. If there's anybody that skis or whatever, they'll probably look at the one on the left. That's the snow. What it is just showing the fraction of the precip that falls. What amount was it snow and what amount was it rain? So the left one is snow, the right one is rain. And that's where you look at these changes that have been happening. Like for example, you see kind of a flat line when it starts out there in October, November, December. Well, if you're looking at the rain, you see 100%. If you're looking at the snow, you see 0. And you see it goes over into the red. That's because snow has been falling at Lolo Pass later into later into the fall than it normally would. So you have rain happening in those early fall months when it, based on 40 years of data, normally would not. And that's the most significant pattern that we saw in the precip, is that you have less rain in the summer, more in the fall, and then the snow still accumulates when you would think it would over the winter, but it's a little more sporadic. And that we'll come back to, because it has important consequences for how water eventually ends up down here in Lolo Creek. So, based on the precip data, I've got a little quiz here to see how people's memories are of flows on the creek. And if you want to use the data, you can. But does anybody have an answer? Which year out of 2016, 17, 18, or 19 do you think Lolo Creek produced the most water? Anybody have a guess? Between those 4 years.
2018.
We got a 2018? Is that pretty unanimous? It was actually 2017. What about the least amount of water? That could be true. It was 2016, which is actually, it was measured going dry in this stretch in August, September of 2016. What about the largest flood?
Out of which years?
Same ones, 16, 17, 18, 19.
18.
18? You'd think. It was actually 2019. Had the highest peak of all the years. Yeah, so obviously it kind of highlights that if you look at just the precip, you would think, yeah, 2018 produced the most water. But clearly it's a little more complicated than that. And the reason for that is now we'll move on to the next part of the story, which is temperature. Temperature is actually really important for water supply and often overlooked. People tend to focus a lot on the precip, but temperature controls two really important things, which is the amount of water that's lost across the landscape, used by the forest, staying in the soil or being evaporated from the soil. Because higher temps, vegetation is going to grow more, it's going to use more water. It's obviously going to evaporate off the soil more. And temperature also controls how the precip is falling, whether it's snow or rain. And we'll talk about that next with snow and why the patterns that exist are actually really important for how you have water supply later in the year. But when we went back and looked at temperatures, we found basically what you would expect supporting what we saw in the precip. We saw an increase in the average daily temperature at the snowtail site. And at first went back and said, oh, well, there's a definite trend. I mean, you can see it on that graph on page 2 of warming temperatures in the Bitterroot. The green line on the bottom is Lolo Pass. from the 80s, it just kind of goes way up once you hit 2000, and it's stayed well above average. I went back to the data and said, well, is that just a blip, or how far can we look back? Well, Hamilton goes back to the 1890s. It shows a kind of a muted trend, but the same thing is it's been increasing pretty steadily 1 to 2 degrees Fahrenheit since the late 1800s. And then you see the same bump happening from the 90s on. You just see a much bigger bump at higher elevation, and that became an important component when we were looking at this. So it's important to keep snow up at the higher elevations, but it's hard to do when the temperature starts getting warmer. And most of that temperature increase we noticed was in the minimum daily. So it's at nighttime. It's the nighttime temperatures that are actually increasing more than the maximum temperature for the day. So the next part is the snow storage. So we talked about snowfall. Snow storage is the stuff that lands up there and it stays there, and that's basically a big reservoir. So that is what melts during runoff and it leaks out later in the year, and how you still have water in the creek in these drier months, because precip is not distributed throughout the year. You know, you have more during the winter at higher elevations, and you have more at lower elevations during the spring. So it's very complicated in the ways that it works across the landscape at different times of the year. So the snow storage is the reservoir, and it's measured in snow water equivalent, or what we call SWE, which is the liquid content. So snow has air in it as well, and that's, again, this data is collected by USDA at the SNOTEL site, but we didn't see any patterns or trends in snow storage in terms of it decreasing or increasing. We just saw that two main things: snowfall, like it accumulating was happening really sporadically compared to in the past. You'd have these big storms and then nothing, and then a big storm and then nothing, rather than kind of steady building up your snowpack. And then we also saw that in the spring, the melt rate was much higher, or much faster than it was, over 40 years ago. So you have much higher temperatures, obviously, at that time of year than you normally would, and it comes off really quickly. And so that can lead to larger floods and more flooding problems, because you're not kind of trickling the water out. So when you combine, there's a lot of other things that go into it, and details that are kind of beyond what we're talking about today, but when you combine the precip and the temperature and the snow storage, these are all these kind of variables that we think about. How does that produce stream flow in the creek? And you can actually go back, like I said, and if you really dig into one of these, pick a year and look at what happened with the temperature, what happened with the precip, it actually all does kind of come together and line up. It looks kind of like chaos with all these lines on graphs, but if you really slow down and pick apart one year, you can see that, yeah, it makes sense with how much water fell and how hot it was. So, which brings us to the stream flow component. And we usually describe kind of a stream's flow that's in it. It's called the flow regime, which is just a term for how much water is in the creek at a certain time of year and how frequently that happens over, several years. And that's basically, you have to have a lot of gauge data to kind of build a data set of how the creek fluctuates from year to year. But I have on the handout just a few quick numbers if people are interested. The 2-year flood, which is a flood that happens once every 2 years, is about 1,500 CFS. The 20-year flood is about 2,200 CFS. Runoff lasts for 120 days. The average annual flow is 257 CFS, around there. And for comparison, the Bitterroot down by Missoula has quite a range of flows, but it peaks between 15 and 20,000. So when you ask yourself, is this a big number or a small number? Comparatively, it's a small number, but you can kind of think of these numbers as unique to their own stream. And it just depends on the issues in the area. Another good one was minimum flows. So 35 CFS is considered an average minimum for Lolo Creek. And when it gets below 30, that's really considered extremely low. Obviously, down here it gets to 0 sometimes. But probably the big takeaways from the stream flow graph that's on there is you can look at the shading in the background behind the black lines. That's 18 years worth of flow data from old USGS gauges and our gauges. So it's kind of a good representation of a century of flows. And pretty much every year except 2017 was early for runoff, and it came off really fast, which supports everything we saw in the precip and the temperature data. So that's kind of the hydrology rundown of what we observed, and the different processes to produce stream flow. The next page is a map for the actual water balance that I talked about in the beginning. And what it is, the lines are scaled, so you see all these squiggly lines running around. A thicker line means there's more water at that point in the creek or tributary, and it's a surface water and a groundwater balance. So you can see, you know, the interaction with groundwater as well, where the creek loses to the groundwater and then the groundwater pushes it back into the creek and things like that. And all of the numbers on here are in thousands of acre feet and I put a little, for anyone that has questions about acre feet or CFS, there's a units thing in the handout too. But really, from the quick numbers on this graph, and this is the accumulation of all that data that I talked about, and the whole procedure that we went through to build this graph is really the product of the project. But about 152,000 acre feet, which is, I think I wrote the number down here, it's 50 billion gallons in an average year. So this is just an average year, what would happen on Lolo Creek on an annual basis. Flows out into the Bitterroot. And then 11,000 acre feet goes underwater or underground into the Bitterroot. And then roughly 12,000 acre feet is used within the basin or exported from the basin. So when I say exported, remember I highlighted those irrigation parcels that are outside, they're to the south of here. This is the important part of that, because normally when you take water out, you use it for irrigation. Crops use actually a lot less water than you actually divert typically. And depending on where you're watering the crops, where your ditch is at, most of that water has the opportunity to end up back in its source, which would be Lolo Creek. The fields that are irrigated to the south of here are in a different topographic area that drains into the Bitterroot. So when you take water out, it has no chance of flowing uphill and going back into Lolo Creek. So when you start looking at, that's that orange arrow on the diagram, you see exported irrigation. That's the water that goes to water things, irrigate things that are outside of the basin. The other exported thing from here is groundwater, which the city has one well that pulls water out of actually Lolo Creek area, and it is treated and put back in the Bitterroot, so it's considered exported too, because you can't end up back here. It ends up downstream on the Bitterroot.
When you say the city, you mean Lolo?
Yeah, the water and sewer district. They have the 3 wells.
Right.
Yeah.
It's not really a city.
Right, yeah.
So the connection between surface water and groundwater replenishing each other, how long has that data been realized?
Upstream of the canyon up here, I don't really know if anyone's really looked at it before.
So when you guys put in the test wells along with the Bureau mines, that was a combination of examination that the surface water, when it disappeared, you also noticed the groundwater disappeared. The drop, correct? There's a direct correlation between the drop together.
Right. That's definitely, so down here, and I was going to get into that. So down here, where we're at, the interaction between groundwater and surface water is different. Here, it goes, in this area actually, and just upstream from us, it goes into the aquifer from the creek, but it doesn't, from our data, it doesn't come back. It flows completely out. So that is the component that Bureau of Mines and Geology we're going to look at, because the controlling the valve on that, we're not sure. And we don't, DNRC's part of this was not to collect that data. Bureau of Mines and Geology, we're going to build a very fancy model where they'd be able to basically dry the creek up they could put water into it, and they could change the level of the Bitterroot, they could change how much people are pumping, they can change all these variables and try and see what dries the creek out. Because that's kind of the issue you run into, is we have all these different factors, and we didn't have the data set to determine that, and you really have to build a model to do that. And so that was going to be their contribution to the project. What you're looking at here was data that was just measured the level of the water underground, and we measured how it changed from month to month, and that change is a volume, obviously, in the aquifer.
So you have some kind of wells that monitor groundwater?
Yep. Yeah, there was 70, 80 of them or something like that. Yeah, quite a few down in this area, and then we had them going all the way up to the South Fork pretty much. There's a couple wells up there. So the interaction between groundwater and surface water, you can see it on here, like you pointed out. You got arrows going down, coming back up. All of that mostly is happening from the South Fork to Mill Creek, and that's just based on the geology. You have there's the irrigation that happens up there too, and stuff goes into the ground, and when it comes into this little pinch up here, it starts pushing back up into the creek, and you see gains from the groundwater right there. And then once it flows out onto here, you see it slowly just trickle out, and then it never comes back. And maybe in the last quarter mile of the creek, when it's practically in the Bitterroot, you might have some flow coming back. But yeah, that's a good point to highlight. I think the other thing to look at this in terms of the surface water is where it's actually coming from. So it was actually split kind of three ways. You had 1/3 of it coming from the South Fork, you had 1/3 of it coming from the headwaters, which would be the East and West Fork, and you had 1/3 of it coming from all the other smaller tributaries as you come down. Graves, Granite, Mill, Woodman, Bear. So all of those contribute 1/3 as well. And then lastly, you probably noticed that this graph doesn't really look like Lolo Creek is hard up for water. You've got this big blue arrow going through there. Wow, there's tons of water. There's tiny little red arrows. Well, I kind of put this graph here to lead you into that thinking. Because when you start looking at actual water use, this is averaged over the year. And there's a different component to that in terms of where you're at and at what time of year. And you can see in the pie chart down at the bottom, I was going to kind of leave that for everyone to look at. It's pretty self-explanatory. That's just of that 12,000 acre feet that I talked about, that's where it goes to. So you can see it's like 53% goes to ag-related use, less than 8 goes to domestic, municipal, and then the natural losses are all of the losses down at this lower end. So that 40% is pretty much occurring down here at this end, not really further up in the basin. And for anybody that's curious, if you take away the natural losses of the aquifer, it's I believe the number is closer to the 6,000 acre feet range that's consumed by various uses in the basin. So it doesn't seem like a lot, but that's kind of the last component of this talk is bringing this all together into the next page 5.
Question.
Yeah.
Question. So in natural losses, is that the water going into the groundwater plus the cottonwood soaking up? Like what is all
Yep.
included in natural?
That's riparian, evapotranspiration, water going into the ground that never comes back. If it comes back, we consider it still connected.
Still connected.
And it's just open water evaporation from the creek, which is pretty minimal when you have shaded areas and things like that. For that 40%, most of that is going into the groundwater from what we measured. There's probably a fraction of it maybe that is from the cottonwoods, but we don't know because of the way that the surface water interacts with the groundwater. We can't tell, is it using creek water or is it using groundwater, the vegetation? So kind of there's some lumping you have to do there, but I would say the vast majority of that is to the groundwater. And when you look at natural losses above this lower section where it loses, it's much lower. It's maybe like 2 or 3%. But this is the basin kind of average. Yeah?
So with everything that was measured, to look at how rapidly things thaw and may or may not end up, draining into was there any weather gauges measuring wind along the way? Because those of us that have lived here 40-some years have noticed a major increase in the winds, which contribute greatly to things drying up
Yep.
much more rapidly. And so I'm not
You're
seeing
absolutely right.
anything. I mean, I've gotten to the point, and I love flying kites, but I've gotten to the point where I curse the wind because it's working against me trying to irrigate.
Yes.
And I consider the water and every molecule valuable and stuff. So it's like, you know.
So both the weather stations do collect wind,
Okay.
I think wind speed data. So yeah, you could go, you can look and see if there's been changes in wind patterns. I didn't see anything in terms of wind up at Lolo Pass,
Okay.
but that it's likely because the instrumentation is in a wooded area where, you know,
Yeah.
even if the wind is blowing, you may not see the full scale of it. The other weather station, the Montana Climate Office one, hasn't really been in long enough to do any of that. Yeah, it's been there since late 2016, so you really get a picture of now, and you can't really see like down lower here what's been going on. And that's just, I mean, that's an issue in hydrology that you run into. Sometimes you just don't know because you don't have the data.
Is that your gauge or yours?
The weather station?
Yeah.
It's Montana Climate Office, which is through U of M. They have a few weather stations here. I think they're building a bigger network of them across the state. But
is that available online? That information?
I believe it is, yeah.
It's on the
Okay.
back of your brochure.
Yeah. So yeah, but no, wind is part of the evapotranspiration. When I was talking about temperature increasing, loss across the landscape, wind will fuel that as well.
Right.
Especially if wind during warmer temperatures, it's going to
Exactly.
be a positive feedback. But anyway, this last page kind of breaks it down into showing you where the water supply issue actually happened. You have to start looking at smaller time scales and then also the geography. So the two bar graphs that are on there are showing what percent of the available water, what's in Lolo Creek, is being used in that month. The months are along the bottom, and then each one of the bars is 2016, 17, 18, 19. So the top one you can see in the box, that's from the South Fork to Mill Creek. And you never are using 20% of what's in the creek. There's not as much use up there, even between irrigation and what homes and things are up there. You're using a very small portion of what's in the creek. Now when you get down here below the Morwen Peak Bridge to Highway 93, then you can start to see August and September. Your supply is starting to exceed the availability. And again, these are monthly. If you were to break it down into daily, you would definitely see some 100% in there. And that is what we call over appropriation. The demand is higher than the water that's actually there. And so I think the big question that DNRC went into this project was is Lolo Creek over appropriated, and when and how? And so from this greater water supply perspective, the answer is yes, in certain years, at certain times of the year. It's not a straightforward answer, but 2016, we'll focus on that one. That's a year that it dried up for quite a long stretch. We measured it to the gauge down at 93. It was a really low flow year as well. Everything kind of, when you look at the data, it lines up and you would think, yeah, that's going to be a year when it goes dry. And that's where you see on those graphs that it's, 98, 99% of the water is being used down on this end. But the thing that we saw when we dug into it was it's not like everybody was watering their lawns or irrigators were taking double the amount of water they normally do. The tricky part about it is the exchange with the groundwater in 2016 in August and September just happened to be a lot higher than it normally was. It was losing way more to the aquifer, and that's where you get into what MBMG is going to be focusing on. Why? What caused that? We can speculate based on the well level data that we have that, yeah, groundwater levels were really low that year as well. So maybe you had an increased gradient between the creek and the groundwater that was pulling more water out of it than normal. But again, we don't really have information on what the Bitterroot is doing, because the water table and the water surface of the Bitterroot probably plays a factor into if the creek dries up for a certain amount of length too in these dry years. And then the last graph on there was for visual purposes. I won't go over it too much, but the blue line on there is the natural, like if we took all use out of the basin, that would have been the monthly flows in Lolo Creek. And then the red line is what the flows actually were, the dashed red line. So you can see, yeah, for most of the year, it's not over appropriated. There's lots of water based on how much use there is, but then you hit these months at the end of the summer where, whoo, the lines start to deviate until you get back into the fall. There's less use. And I think ultimately, everything that I talked about today, it's not really unique to Lolo. And that was kind of the part of putting this in like a greater context, but certainly Lolo has its own geologic setting and its own characteristics, but what we see in terms of the precipitation, temperature, all these patterns, is stuff that hydrologists all over the West have been seeing in the Colorado River, the coast, and mountains all over the West, is that stream flows are going down while precip isn't really. And it tracks more with these other meteorological variables like temperature, maybe wind, things like that people don't normally think about when they think about droughts. And so the question of why Lolo Creek's been drying up more frequently in the last 20 years, when you look at those temperature graphs I showed you from about 2000 on, that period where the temperature spikes up all across the West has a name. Hydrologists have termed it the turn of the century drought. And based on tree ring data, so another method that hydrologists use, they can reconstruct water supply by going back and looking at thickness of tree rings to see how much water there was. That'll take you back 2,000 years. And the turn of the century drought is one of the worst in 2,000 years based on tree ring data. So is water use a factor playing into this? Yes. Water use is not changing in Lolo Creek rapidly enough, and it really doesn't hold a candle to these natural climate signals that control water supply when you look at it in the grand scheme, which is that average line that looks like there's tons of water. So that was kind of the interesting component of this as well. It lines up well with water supply issues that are happening across the West based on patterns that we've been seeing. And I think there's actually some more recent stuff that came out that looked at recreating soil moisture and forest fire over a 2,000-year period as well, showing that those really high elevations up in the Alpine are starting to dry out to the point where they've documented fire scars in places that haven't been there for centuries, or never burned maybe. So. Think, yeah, go for it.
I was wondering if the models that the Bureau of Mines are going to make would be useful in predicting when the droughts or like dewatering could occur, and if so, what could, I don't know, how DNRC's policies might change in the future to address the climate issues that we're seeing rather than the water use issues that
Sure. No, that's great. This is the next component, which is addressing water supply issues in basins like this. So again, Lolo Creek actually, in terms of the setting, this type of natural loss problem that happens down here in this aquifer where we're at, that also happens in lots of places across the Rocky Mountains. You have tributaries that come out of these steep drainages in the mountains into a big broad valley, and they have to cross really thick material, porous material, to get to the bitterroot, say. And that can obviously pass a lot more water than bedrock or what's up above. And so it is a problem that you run into in a lot of situations where you have municipalities or irrigation right at the mouth of the tributaries, because there is a concern, and people want to keep creeks flowing and connected, especially ones that are sensitive for different habitat or environmental concerns like Lolo Creek. But you have to contend with these natural losses that are built into the system, basically. And so when it comes to managing that, my last part that I have here is, what are some solutions to this? And I guess I'm thinking about your question here in terms of DNRC's policies and things like that. And I'm not the policy maker at the head of it to decide how DNRC reacts to issues like this. But there are some methods that you can try to keep creeks like this connected and also supply the necessary water that people need and use in the basin. So, and a lot of these examples come from other places too that are doing this. So one example is what in other states they call a water exchange. So if you have a high use user, say ag or something, that diverts in a situation like this and exports water out of the basin and never comes back to Lolo Creek, a water exchange would allow them a temporary right or permit to pump out of a more voluminous stream, which would be like the bitterroot. So a water right on Lolo Creek is probably small for the flow in the bitterroot right now at this time of year. So to be able to have an operation where they could switch their source, and then their water right would normally just run down Lolo Creek and then go back into the bitterroot. There's a lot of complicated factors involved in that, and determining if them pumping from a different point hurts another user, which is part of the process. So this is actually done in Idaho, and that they go through a whole process of determining, are they going to hurt another water user if we do this? But it has been successful at keeping creeks connected, because our water right is only 15 CFS and there's 1,000 down there, and then they only take 15 CFS out for a half-mile stretch, and then the tributary comes back and it's there. So that's one solution. Problem with that solution, it's illegal in Montana. Can't happen, especially here in the bitterroot. This is a closed basin, closed by the legislature. So you can't change a point of diversion or really do much with the surface water right here. There are exceptions to the closed basin, but none of them really allow you to do something like a water exchange. And we don't really have a process for temporary water rights that would allow someone to, say, pump to keep the creek connected for the month of August or September. So in terms of DNRC changing on that one, it would take a change in law, statute and rule to make something like that happen, which I can't do. That's above my pay grade. But another one, which is probably the most obvious in a situation like Lolo Creek, that is done maybe to some usually to detriment, is storing water. A reservoir. That's why people started building reservoirs, to capture water when it's there, release it when it's not there. It's the same way snowpack works. Fortunately, like on-channel reservoirs typically cause a lot of problems that come along with that. They would go against a lot of other conservation and habitat goals that are going on Lolo Creek right now. Also, you'd probably have to flood people's homes to put an on-channel reservoir on Lolo Creek. So oftentimes, especially nowadays, it's not a popular option or a very practical option in most cases. But One other reservoir solution that is actually legal under the closed basin would be an off-channel reservoir, well, and it wouldn't be as detrimental to the ecosystem itself, would be off-channel storage where the water's being used, because there is an exception for that to take flow during high flows, store it for later in the year, which would be available to irrigators when the creek got so dry, they could just start using that stored reservoir water and let the creek flow and not divert from it. Likely expensive, would take a lot of assessment to see if it's practical, possible to build. You'd have to build reservoirs up to the south of here where all of the irrigation is for something like that. So that would take probably some time and effort to determine if that's a solution, but it is something that would be feasible under how law and rule is situated with the state right now.
Well, and some of that, when you're talking irrigators and stuff, for the most part, all the ones I know come from a gravity-fed ditch.
Yep.
And that, aside from the man labor that's involved in maintaining those ditches, opening and closing them, and so it's not very labor intensive and it's not very expensive when you talk about water storage, unless it's like stored somehow so it still can be gravity fed into their systems that they use for irrigation.
That's what you'd have to do
There's
probably,
expense.
so that they don't have to switch their systems out.
Exactly. Okay.
Yeah, and that's what I'm saying. You'd have to do some sort of site assessment to see, like, could it be physically done with, is there space for reservoirs? Is there, can they be used with current systems, things like that.
So, what about wetland restoration up on the forest?
Yep, so these are changes like to just general water use. And that is the second part of your question, which is how do you fight against the changes that we have no control over? I mean, you know, at least at this point in time, like we can't turn the thermostat down and stop excessive loss across the landscape. For that, talk about this last, just sort of like general solution that I have, and then we'll talk about that one. And the last one that I had was in a setting like this, in-stream flow rights, which I believe the Clark Coalition is doing on Lolo Creek, but there's a host of other debates and issues that come along with the retirement of ag land for development and things along those lines. But when you have a reach like this, where even most irrigation that would happen out here probably goes into the aquifer and likely flows out just like the creek water that goes down there, in-stream flow rights become a really practical thing, because it's less about, oh well, we'll still get the return flow. In this case, you may not, and so keeping it in channel may actually be the best thing. And so things like converted water rights or leased water rights, things like that, are actually a pretty good solution in a setting like this. There's debate on whether they are in other places where you have strong return flow components and flood irrigation works closer to the creek with the aquifer and things like that. But here, that would actually be a viable solution. And obviously why people are pursuing it. So yeah, changing natural conditions. The only one I really had for that was natural storage, which is the idea that you kind of engage these reservoirs that already exist in nature up in the basin and figure out how you can, I don't want to say control them, but work with them. So the example of wetland restoration, most examples of this are, there's really three things that are done, which is engaging floodplains, beaver mimicry, way up in tributaries, and restoring wetlands, oxbows, bins like that. All of those things engage the aquifer more, and you can, you know, have places across the valley bottom to store this water and leak it out slower through the groundwater rather than just sending it straight down the channel. So in terms of, you know, changing policy, DNRC recognizes natural storage as a way to combat changing conditions across the state. So I think the biggest thing with it is there's just not a lot of information on how effective is it in a place like Lolo. What would it take? Could you actually use it as a management tool, or would it be too unpredictable to actually